Okay, so we will start. We will start Fourier transform. Okay, Fourier transform of a discrete time signal. Okay, so you already know that Fourier transform we normally use for non-periodic signal. Non-periodic signal. You maybe remember that in case of continuous time signal, we have derived this Fourier transform using continuous time Fourier series representation. I hope you can remember it. Okay. But here we are not going to do any derivation. Okay, so we will use the Fourier transform identity. Normally we call it Fourier transform pair. No? Can you remember? In case of continuous time signal, we have Fourier transform pair. Okay, so directly we will use this pair. No, pair. Okay, transform pair to continue our discussion. Okay, because the derivation is not much important for this course. Okay, so Fourier transform pair, just give me a moment here. Okay, so you already know that if we have, okay, if we have a discrete time signal xn, okay, so this is a discrete time signal nxn, okay, so you know that we can say this is a time domain signal, no? Time domain signal. Any issue with this time domain signal? This is n is not time, no? So do you have any issue with this? Sometimes you may feel that this is not time domain signal, no, because here we have sample, not any time value. So how can you justify it? How can you justify this is a time domain signal? Can anyone remember? So if you can remember, you can tell me. We can view this as a time domain signal, no? How? අපිට මේක බලන්න පුළුවන් time domain signal එකක් විදියට. කොහොමද එහෙම බලන්නේ? How we can see it? Because this n is always mapped with t, no? Can you remember? This n is always mapped with t. Okay, so you know that t is equal to nts. Can you remember this? Okay, okay, so this n is the number of samples. So this n is a number of samples, so always n. So here, sorry, here capital N, I will use simple n. So already you know that t is equal to nts. Okay, so this is number of sample, nth sample, and here it is in sample. So you can see that in sample is mapped with time. Okay, so basically this is a time domain signal. Okay, so this time domain signal, you already know that if we get the Fourier transform, we will have frequency domain signal, no? Can you remember in case of continuous time signal? Okay, if we get the Fourier transform of time domain signal, we will have the Fourier transform of frequency domain signal, and we denote it as like this, no? Can you remember? Okay. So here instead of this omega, okay, I will use capital omega because to represent uh, to to distinguish with uh, continuous time signal, no? So here we have used n in continuous time signal. You can remember that we have write this as like this. Okay, can you remember? This is capital X, omega like this now. So this one, so here t omega, we will use simple n omega. So instead of omega, I will use the capital N omega. Okay, so that is the difference. No any much definition is there. Okay, instead of simple omega, I have used the capital omega here to represent our discrete time signal. Okay, so this is the Fourier transform of this signal. So if we have xn signal, if we get the Fourier transform, we will have frequency domain signal. Okay, so you know that this is a frequency domain signal. Okay, and already know that if we get the inverse Fourier transform, okay, if we get the inverse Fourier transform of this x omega, okay, we will have the xn, the time domain signal again. So if we get the Fourier transform, we will have frequency domain signal. Okay, it is time domain to frequency domain conversion. Okay, so if we get the inverse Fourier transform, it is frequency domain to time domain conversion. Okay, so you know that this is time domain. Okay, this is time domain, and if you get the Fourier transform, you will have frequency domain signal, and if you get the Fourier transform of inverse Fourier transform of this frequency domain signal, you will have original time domain signal. Okay, so here it is Fourier transform is time domain to frequency domain conversion. Okay, and inverse Fourier transform is that frequency domain to time domain conversion. Okay, so this is the Fourier transform pair. Let's see what are the identities we can use to calculate the Fourier transform and inverse Fourier transform. So, this is the identity for Fourier transform, the forward Fourier transform. So we will have uh, capital X omega. Okay, capital X omega. So it is a frequency domain signal. Okay, so frequency domain signal we get if we get the Fourier transform of this time domain signal xn. Okay, and the identity is minus infinity to plus infinity xn e to the power minus j omega n. Correct? Okay. Is this the Fourier transform? So can you, if anyone, so any of you doesn't have any issue with this statement? So this is a discrete time, no? This is not continuous time. This is discrete time. Okay. So this signal is discrete time signal. For discrete time signal, should we do the integration? Should we do the integration? No, we no need to do the integration. Okay, we already seen these things. Okay, we can get a simple summation of that point. Okay, so no need to get the integration here. Okay, you can get simply a summation. Okay, you can get simply a summation here. Okay, so you can get simply a summation here. The summation should be n from minus infinity to plus infinity. Okay, so this is the identity or statement for Fourier transform. That means we have convert this xn time domain signal into frequency domain signal into x omega. Okay. Okay. So inverse Fourier transform. Okay, so this is the Fourier transform. Okay, so if I write this right way, I think it is more understandable. Okay, so if we get the Fourier transform of this time domain signal xn, we will have the Fourier transform frequency domain signal, that is x capital omega, capital X capital omega. So this is the identity for Fourier transform. So this is a Fourier transform. Okay. And what is the inverse Fourier transform? Inverse Fourier transform is, so we have to get the inverse Fourier transform of this x omega, no, frequency domain signal. So Fourier transform, you know that time domain to frequency domain conversion. Okay. And you know that IFT, inverse Fourier transform, is frequency domain to time domain conversion. Okay. So you already know that the frequency domain conversion, the frequency domain signal is this one, capital X omega. So if you get the inverse Fourier transform, let's denote this, it as like this, f minus 1. So this is the inverse Fourier transform. And inverse Fourier transform of x omega, okay, that is, we have xn again, no? We have our time domain signal. That is, we have 1/2 sigma within 2 5 capital X omega e to the power j omega n. Okay, is this okay? Is this statement okay? Okay, so if you get, so this is definitely a discrete time signal, no? So this xn is definitely a discrete time signal. Okay, so if you get the Fourier transform, you will have some kind of signal, frequency domain signal, x omega. So can we tell this x omega? Okay, can we tell this x omega is a discrete time signal? Can we directly tell this is a discrete time signal? Yeah, discrete time signal xn. හරි. අපි එයාගේ Fourier transform එක ගන්නවා මොකක් හරි කරලා මේ විදිහට සිග්නල් එක අරගෙන ඒක මේ e වලින් වැඩි කරලා සමේෂන් එකක් ගන්නවා. ගත්තාම ඒ එන සිග්නල් එක අපිට discrete time signal එකක් කියන්නම පුළුවන්ද? එහෙම බැයිද කියන්න? So can we give a certificate that this is a discrete time signal or not? We can't give, no, because we don't know. Here this one is discrete time, okay, but after converting it to frequency domain, we don't know this frequency domain signal. Okay, it is depend on this xn, no? For different xn we will have different kind of frequency domain signals. Okay, so we can't guarantee, no, we can't guarantee that this x omega, this x omega is definitely a discrete time signal, no? So this x omega we can't guarantee, no, we can't guarantee, okay, guarantee that x omega is discrete time signal, no? We can't guarantee it. Okay, sometimes it's not happen. Okay, sometimes this may be a continuous time signal. So this x omega we can't tell as a discrete time signal. It may be a continuous time signal also. Okay, so this statement is somewhat wrong. Okay, this statement is wrong, this one. Here we can't put summation because we don't know this x omega is, we don't know this x omega is actually a discrete time or continuous time. Okay, maybe it may be a continuous time also. So here we have to apply the integral. Okay, Integral should be within 2 5. Okay, and it is with d omega. Okay, so these are the two identities for Fourier transform and for inverse Fourier transform. Okay, so you have to keep remember these two identities. Okay, so already you have. Okay, so these are the identities. Okay, so you have to remember this. Okay, and also I would like to discuss few properties this time. Okay, this time also. Okay, mm, yeah, okay, I will discuss few properties, not discuss, I will state few properties. Okay, so these properties we have learned in continuous time Fourier transform also. Okay, and here also I will put that property here. Okay, so one property is important property is linearity property. Linearity property. Okay, so what is linearity property? You already know that. Okay, so I don't think I have to explain it much. Okay, because these things we have seen in case of continuous time signal. Okay, so I hope you can understand this. Okay, so linearity property, first one. Okay, so you can note down this. Okay, so linearity property said that as usual. Okay, if we have one signal, okay, and if you have another signal, and if you get the Fourier transform of this one and Fourier transform of this one, if we have capital X1 omega and capital X2 omega. Okay, so you already know linear property. Now I think you can understand. If we have to find the Fourier transform near a1 x1 n plus a2 x2 n. Okay, this kind of x, that means that the summation of these two signals, the combination signals. Okay, if you have two separate signal x1n x2n, Fourier transform is x1 omega x2 omega, and if we get that signal one and both signal weighted with some coefficients and combined together, okay, then that resultant signal Fourier transform also will be a1 capital X omega plus a2 capital X omega. Okay, so I hope you should know this. Okay, you should keep remember this. I hope you can keep remember. You already you know this property. Okay, this is linearity property. Okay, okay. The other property is I want to discuss time shifting property. Okay, time shifting property. Time shifting property. Okay, time shifting property. So in time shifting property, you already know that. Okay, this one also you know that time shifting means we are shifting times. Okay, so if we have xt, if we time shift the time by t naught, it will be t naught, no, like this. So if we have some signal like this, if we have t naught here, it will be like this. It will be shift to this way. If this is plus, it will be shift to this way. No, can you remember? We have done some time manipulating things. Okay. So, okay. So time shifting property said that if we have xn and the Fourier transform of xn is capital X, capital omega. Okay. So if we have time shifted signal in my k like this, okay. So that time is shifted by k. Okay. So we have we have mm, okay, we have Fourier transform of okay e to the power minus j to 5n. I put capital N here. Okay, don't worry at this time. I put capital N here, but is you can see that no capital N is here. No? Okay, anyway, this is capital N. Okay, and it is x omega. Okay, this x omega. Okay, so time shifting property we will have like this. Okay, so just keep remember this. Okay, I will tell what is this and what why I put n here. Okay, so up to this level you should just keep it in memory. Okay, and the third property I want to tell you is that frequency shifting property. Okay, frequency shifting property. Okay, in frequency shifting property it is said that I'm sorry, wait a minute. Okay, so I think this is not here n is come to the DFT. Okay, not this discrete time Fourier. So this is simply n. Okay, I'm sorry. Okay. Here you have the frequency shifting property x n minus n naught. You have e to the power j omega n naught. So this is minus. Okay, e to the power j omega n naught x capital, sorry, capital X capital omega naught. Okay, I have mistake with x omega. Okay, so this is the frequency, the time shifting property. Okay, so let me check it. Okay, so hold on please. Time signal, you can see my screen. Okay, so I will use that books as usual. So here you have Fourier discrete time signal. Actually, I couldn't keep this property in my mind, but you have to keep them, okay? Until the exam at least, okay? So here properties of Fourier transform, okay? So we will see. So you can see that here x n by n naught e to the power minus j omega n naught x omega, no? Yeah. So here we have k, get k, so it is x n minus k e to the power minus j omega k. Sorry, here k. Okay, k x omega x omega. Okay, so this is our frequency shifting property. Sorry, time shifting property. And in frequency shifting property, we said that okay, frequency shifting properties is stated that if we have xn signal, time domain signal, and if we get the Fourier transform x omega, okay, and if we have another time domain signal, that signal is multiplied by e to the power j omega naught n, okay, age omega naught n, then we will have the signal x omega minus omega naught. Okay, so these are the three properties we are going to learn. Okay, linearity property, linearity property. So this is linearity property, time shifting property, and frequency shifting property. Okay, so we will see these things in later on also. Okay, so just keep in mind, I think you can understand this, no need to do any verification. Okay, you have to keep this in your mind. Okay, these three: linearity property, time shifting property, and frequency shifting property. And in our reference book also you can see the in solved question. Okay, in solved question, solved problem, Fourier transform, you can see that here the time shifting property is verified. Okay, you can refer this. Okay, it is not much easy, it is not much difficult. You can, I hope you can understand it. Okay. And also I hope the frequency shifting property also should be verified here. Okay, yeah, this one, frequency shifting property, the verification. I think that much, that one also not much difficult. You can get idea. Okay. Uh, okay, now we will get one example. Okay, we will get one example. So so basically these are the things you should know. Okay, we discuss up to this level, this Fourier transform, discrete Fourier transform, uh, uh, transform. Okay, discrete signal Fourier transform. That is, you have to you should be able to use this identity, the first principle identity, and also this property, this three property actually. Okay, linearity property, time shifting property, and frequency shifting property. So